Hello again. In this video, we're going to talk about the column space and the null space of a matrix. Subspaces of a matrix usually occur in application and theory in one of two ways. In both cases, the subspace can be related to a matrix. So the first way is the column space. So let's look at the definition of a column space. A column space of a matrix A is the set column A. That's the notation of all linear combinations of the columns of A. Let's look at, we have a couple of notes here. The first note is, let's let A be an n by n matrix, where A is the set of vectors A1 through AN, where each AI is an Rm, which makes sense because there's m rows. Then the column of A is just the span of those vectors, of the columns of A. Makes sense because it's the linear combination of all the columns, which is exactly what our definition of span is. We actually saw in the last video that the span of p vectors, in this case we'll just have n of them, is a subspace of Rm. So you can check that out. Note 2, the column of A is Rm, the whole thing, if the columns of A span the whole thing. Makes sense. So let's start with an example in the book, example 4. So example 4 states that if you have a matrix, here it is, and a B, determine whether B is in the column space of A. So in other words, we want to know if B is in the column of A, where the column of A is, oh, I forgot the word span, is the span of A1, A2, A3. That's better. And by the way, where A1, A2, and A3 are the columns of matrix A. Okay, so in other words, we want to know, is B a linear combination of A1, A2, and A3? So let me write that. So is B equal to some C1A1 plus C2A2 plus C3A3 for some scalars C1, C2, and C3? Well, the answer is yes, because if you re-look at this, this would be C1 times the A1 plus C2 times the A2 plus C3 times the A3 equals the B. And we can put this in matrix form and solve for C1, C2, C3. So let's go ahead and do that. If we row reduce this, what do we get? Taking 4 times row 1, adding it to row 2, you should get 0, -6, -18, and 15. And then doing the same thing with the last row, taking 3 times the first row, adding it to the last row, you should get 0, -2, -6, and 5. Now I'm going to switch those second and last row. And then I'm going to get a 0 here. We conclude that this last row is all zeros. So therefore, there is a solution. This is consistent. If this was a number here, it would not be. So we know that we have some constants C1, C2, and C3, that's actually 3, that satisfies this equation. So we conclude that AX equals B is consistent. If you noticed in the get-go, this was the same matrix for the equation AX equals B. So just another way to say it. So therefore, B is in the column of A. So this example shows that when a system of linear equations is written in the form of AX equals B, the column space of A is the set of all B for which the system has a solution. Very similar to what we did in chapter 1. The next definition is the other space we're going to use a lot, which is the null space. So let's look at the definition of that. The null space of matrix A is the set null A, that's what it's denoted, of all the solution of homogeneous equations Ax equals 0. In other words, the null of A equals the set of x such that Ax equals 0. When A has n columns, the solution of Ax equals 0 belongs to Rn. And the null space of A is the subset of Rn. So in fact, the null of A has the properties of a subspace of Rn. Let's go ahead and see that. The null space of an m by n matrix A is a subspace of Rn, is theorem 12. So equivalently, the set of all the solutions of a system Ax equals 0 of m homogeneous linear equations and n unknowns is a subspace of Rn. So to prove that it is a subspace, here's the proof the book gives here. We need to show the three properties. 1, 0 is in there. And we know 0 is in there because if you take A times 0, right here, it shows it is equal to 0. So that is in the null of A. Secondly, we need to show that it's closed under addition. So let's go ahead and do that. So we need to show if U and V are in the null of A, then you add them together, it's in the null of A. And they did that here. So suppose, right, so it starts right here, to take any U and V in the null of A. So that, what does that mean? That means AU equals 0 and AV equals 0. So then if we look at AU plus V, that's just AU of AV, which is 0 plus 0, which is in 0. That proves it. Thus, U plus V satisfies AX equals 0, so therefore U plus V is in the null of A. Thirdly, it's closed under scalar multiplication. So we want to show if U is in the null of A, then CU is also in the null of A for any scalar C. So it starts right here. Also, for any scalar C, let's look at ACU. We can bring out that C to get CAU from the properties of matrices. And this we know from above is 0, since U is in the null of A, which is also 0. So that shows us that CU is in the null of A. So we showed our three properties here for a subspace. So this proves that the null of A is a subspace of Rn. So let's now talk about what a basis for a subspace is. So I'm just going to read the first paragraph of the book here. Because a subspace typically contains an infinite number of vectors, some problems involving a subspace are handled best by working with small finite set of vectors that span a subspace. The smaller the set, the better. So it can be shown that the smallest possible spanning set must be linearly independent. Which brings us to the definition of what a basis is. So if you have a basis for a subspace H of Rn, is linearly independent. A basis is linearly independent set that spans H. That's what a basis is. Note that the basis is the smallest possible set. So they have an example here for E1, E2, all the way to En. Those are linearly independent. So therefore, the set E1 through the vectors En is called the standard basis of Rn. And let me just read this here. The columns of an invertible n by n matrix form a basis of all of Rn because they are linearly independent and span Rn by the invertible matrix theorem. So there it is. Let's look at this example. Find the basis for the subspace spanned by these three vectors. We know that this is a wide theorem. We know that this is dependent. So the basis would be just these two. I can clearly see this here, that this is a multiple. The first two The second is a multiple of the first, and so we don't need both of those. So note that the basis is the smallest such set, where when you span them, you get the same thing that you would get if you spanned all three. And you will see in the next section that this, the Greek letter beta, is what they use to denote for as a basis. Let's look at example 6. Let's find a basis for the null space of the following matrix. So again, the null of A is the set X, the vectors X such that AX equals 0. So I'm just going to look at A0. So I'm just going to row reduce this. I'm going to switch the second and first row. Now I'm going to get my zeros underneath my first pivot. First, multiplying the first row by 3, adding to the second, we get the 0. We get another 0. We get the 5. 9 plus 1 is 10. Negative 3 plus negative 7 is another negative 10. And then I'm going to do the same thing. We'll erase that and make that a negative 2 times our first row added to the third row. And there's where I get the 0, another 0. Get a negative 4 plus 1 is 1. Negative 4, I said that wrong, plus 5 is 1. Negative 6 plus 8 is 2. And finally 2 plus 4. Uh-oh. That was supposed to be a negative 4 originally. So let's change that. So now I get 2 plus negative 4 is negative 2. I'm going to go ahead and divide that second row by 5 to get the... And I realize that, therefore, I just get a row of zeros at the end when I get the 0 here. And now I can see I have a bunch of free variables. x2 is free, x4 is free, x5 is free. So I'm going to go ahead and get a 0 here, because it's easier when you have free variables to get the reduced echelon form. By multiplying the second row by negative 2 and adding it to the first, you can see here you would get a 0. And this would be a negative 1. 4 minus 1 is 3, and a 0. So as I was saying earlier, x2, x4, and x5 are free since there's no pivot. So I'm just going to solve for x1 and x3. And finally, I'm going to go ahead and write this in parametric vector form. So I will get, or, so these vectors right here are the vectors that form the basis. Because if you notice, we're writing this as, so x can be written as some x2u, where x2, x4, and x5 are in R, so they're scalars. Whoops, that's not a vector. So this shows that the null of A coincides with the set of all linear combinations of u, v, and w. That is, u, v, and w generates the null of A. So that would be, this is your basis. So your basis would be u, v, and w. That's the answer. If you look back at the beginning, it said find a basis for the null space of A, and we just did it. In the next video, we'll find a basis for the column of A.